Okay, so we're going to look at a probability example where we're given a table and we want to go through and find related probabilities. First, when choosing one person at random from the table, and then from choosing two people either with or without replacement at random from the table. Okay, so considering the following table and find the related probabilities. So we have full-time and part-time students, and then we've separated them into who drives to school, and who takes transit. And I'm using FT for full-time, PT for part-time, D for drive, and T for transit. And the first thing when you have a table that you want to do is extend your table to include the totals. So the adding up the total amount of people who drive, 63, total amount of people who take transit, 37, the total part-time students, 30, the total full-time students, 70. And then you should make sure that the 70 and 30 and the 63 and 37 both add to 100, and they do. You know, I'm choosing 100 here. It's just going to make our computations easier throughout the whole problem. It could be any total of people. It's just to simplify the example so that we can learn to understand the concepts. Okay, so here's the question. Given this table, and again, always when you have the table, go ahead and extend your totals. I have three parts here, but the first part says choose one person at random and find A, B, C, D, E, F, G, H, I. Lots of different things. For part two, a few less. Choose two people at random with replacement. And then part three, choose two people at random without replacement. So, you know, if you wanted to pause and write down the table and copy down part one, probably takes like 1 page to do. So choosing one person at random, find the probability that they drive. So the probability that they drive in choosing one person, we look over at the table. At random, we could get any one of these 63 people out of the total number of people, 100. So that probability is 63 out of 100, or 0.63. The second part, probability that they are part-time. Again, I have the notation, the probability of part-time. So that's why I used two letters, PT, as opposed to just P, to avoid the confusion with probability in front. The probability that they are part-time, well, we have 21 who drive and 9 who don't, for a total of 30 that are part-time. And in this initial section, you know, the tricky stuff is coming when we look at the and the or the conditional probability to follow. So those are coming up. But probability of those who are part-time, 30 out of 100, or 30%. The probability that they are full-time and that they use transit. So here I have an and again, I can just write that out, probability of full-time and transit in the notation. That notation is worth a point. And when I go over to the table, you know, I could use a formula, but I would suggest that we don't. We just think about which students are full-time and use transit. Well, it's these 28 students here who are both full-time and use transit. So the probability that they're both full-time and use transit is 28 out of 100. I could reduce that fraction or just represent it as a decimal, 0.28. Moving along. And again, pause at any time if you need to pause and sort of figure out what's going on with that particular part. These are the harder parts. The probability that they use transit or are part-time. So here I want to focus on the keyword or. Again, I'm going to try to avoid using a formula. I'm just going to try to figure it out from the table. So who's transit, or who uses transit or are part-time? So first off, who uses transit? These two groups of people use transit, the 28 and the 9. So I'm going to go ahead and add those together separately. 28 plus 9. And now there's no one else who uses transit. Is there anyone else who's part-time? Well, part-timers are here. So that's these people, the 21 and the 9. And notice if I make them red, you know, the formula would have us, you know, add the totals and then subtract off the overlap. We don't need to. We can take the 28, add the 9, and then add whoever else there is. In this case, how many more people? 21 more people. And those three squares in the table give me everyone who is either transit or part-time. And then when we use the or, it's the inclusive or, so there's an implied or both. And that's out of 100. And then we total that out, it's 58 out of 100, or 58%. I'm going to do another one of these or ones because it tends to be where people struggle. Find the probability that they drive or are part-time. So now we're looking at the probability that they drive. So again, in the table, that's, I could go for the 63, but let's do them each area, each number of people separately. So I have the ones who drive, we have 42 in the first square, plus 21 in that second square. And then we want that or they're part-time. So in addition to these 21 who are part-time, there's again 9 more over here who are part-time. So I have the 21 who are part-time already, excuse me. I need to add in these other 9. And in this case, it's the 21 people who I don't need to count twice. So I add those 3 squares up, and I get 72%. Who the probability of that they drive or are part-time. Next one's a conditional probability. The probability that they drive given they are full-time. So that looks like this, drive, and then again the vertical bar is given that they are full-time. So now maybe I'll create a little more space here and use my pencil. And if you can see his tail, but there's Rio checking in. Yep. See you later. Okay. Nope. So in my work here, generally when we do conditional probability, again, we could use a formula, or I can set up a fraction bar and look downstairs at how many people are full-time total. So full-time total is this first column. I'm sorry, row. No, stay. Okay, so out of them, total, there are 70 who are full-time. So I'm going to put that downstairs in this fraction. Get back there. There we go. And then upstairs, I'm going to ask, you know, what quantity of them drove? If I can get my pen to work. Oh, sorry. Okay, we're going to start that over. Let's see if I can redo some of that I just erased. No, I don't want that guy. Okay. Downstairs, how many people are full-time? 70. Upstairs, how many of those 70 drove? That's what I was trying to do. And I need to look back at my table here to do that. Of these 70 people, how many of them drove? 42. So down in my table, my fraction, I have 42 out of 70 who are full-time. No, sorry. The probability that they drove, given that they're full-time, is 42 out of 70, or 60%. We're going to do another one of these, so hopefully it won't bog me down like that again. Okay, same thing. I want to create a little more space. It's changing my lettering, but it'll fix in the next page, so that's fine. What's the probability they are part-time given that they use transit? So I'm going to pull my table down a little lower so you can see it still. and the probability that they are, excuse me, part-time, given that they use transit. So again, when I set up my fraction, I want to think about the denominator first. And in my denominator, I want to look at everyone who took transit. So that's the second thing. That's the thing that has already happened. How many people took transit? There are 37 people total who took transit. And of them, we want to know how many of them are part-time. So this thing on top, we no longer look at the whole table. We're only looking at the column that deals with transit. So in this column, 37 of them total. How many of them are part-time? Oops. Let's see. So these are the part-time people who took transit. So 9 of them are part-time. So in my fraction here, denominator is 37, and the numerator I can get there is 9, or 9 out of 37. Is my probability. They are part-time given that they took transit. 24%. Make sure that's right. Yep. Okay, so this next question says, let's move myself up, and I can move this table down. Over here. This next question says, according to the table, are driving and being part-time independent? So two things are independent if knowing one has occurred does not affect the probability of the other one. So driving and being part-time are actually not independent. And the reason is, if I think about what's the probability of being part-time given that you might have driven. So again, in this problem, I would look at the denominator first. How many drove? 63. Of those, how many were part-time? 21. So probability of part-time given that you've driven is 21 out of 63, or 33%. The probability that you're part-time, in general, there are 30 part-time students out of 100, or 30%. So because these things are not equal, we know that these two events are not independent. Or restated here, thus, probability that part-time given that you've driven does not equal the probability of part-time. In other words, the fact that I've driven affects the probability. So the fact that I driven to school means it's more likely that I'm part-time. Hence, these two things are not independent. And maybe I'll just put a side note over here. You know, when would it be independent? It would be independent if the probability of, let's say, B given A, this is one of the things that gives us independence, equals the probability of B. So the fact that one event has already occurred does not affect the probability of B. So because that's not true in this case, these two things are not independent. Mutually exclusive is something different. I'm going to move myself over here for a minute. According to the table, give two pairs of events that are mutually exclusive. So, you know, in life, these things may or may not be mutually exclusive. But in terms of our sample of 100 students, it wants two things from the table that are mutually exclusive, or two things that cannot happen at the same time. So the picture of mutually exclusive events would be, if A is over here and B is over here, and they don't have any people in common. Another way of saying that is that the probability of the intersection is 0. Okay, so two things that are mutually exclusive. Well, in this table, you either drive or you take transit. So there's no students that do both, driving and taking transit. So in this table, there's 63 students who drove, 37 who took transit, and those two sets of students are mutually exclusive. Additionally, this pair of values, full-time and part-time, are also mutually exclusive. This maybe makes more sense. You're either a full-time student or you're a part-time student. You're not both. So those are mutually exclusive. Okay, now we're going to move on. Problem 2 is slightly different. It says, choose two people at random with replacement and find the following probabilities. So when we talk about with replacement, we are asking about whether or not there's independence between the two choices. So in this case, the fact that we're doing with replacement will mean that these are independent choices. And so when we have a probability of A intersect B, and this will equal probability of A times the probability of B. Again, that's another one of the conditions of independence, that when you look at the probability of their intersection, it's the product of their probabilities. So for each of these choices, we're going to take one student out, find the probability of something, and then you put them back in and you find the probability of the second thing, and the resulting probability is the product of the two. Let's look at what happens. Move myself back over here. Okay, so find the probability they are both full-time students. So the probability of the first one is full-time, 63 out of 100. And I'm going to multiply that by the probability the second one is full-time. And I put this person back in, so there are still 63 people out of 100. And then I'll let the calculator do the math on that, 0.39. Or if you were rounding to 2 decimal places, that'd be 0.40. Probability that one is full-time and the other one uses transit. Sometimes we have to be careful. If we weren't replacing these people, we would care about which one was first and which one was second. But because we're putting the person back in, it doesn't matter which one you take first. So probability one is full-time. Again, that's 63 out of 100. And I'm going to multiply that by, a little typo there, 63 out of 100. And we're going to multiply that by the probability that they took transit, 37 out of 100. And we'll just go equals, let our calculator do the math, 23%. And the probability that neither drives. So just to save myself trying to figure out how to get a bar over the driving, I could write not drive and not drive. Or I could write capital D with a bar over it for each case. This was easier to type. If I was writing, I might just put in the D with the bar over it twice. So they don't drive. How many don't drive? Well, 37 out of 100 don't drive for the first person. And then because I'm replacing that person back in, it's 37 out of 100 for the second person. So these first three problems are very similar to the top. Number one, it's just you're doing it twice and you're multiplying the probabilities. Oops. The next one asks about the probability that one drives and one uses transit. So one drives, 63 out of 100, and the other uses transit. Again, we put the one back, so we still have 100 people, 37 out of 100. Well, I guess it depends on the situation, but sometimes when it doesn't say, or when we have particularly large numbers, we assume it's with replacement. I will try to be careful to always specify, with or without replacement. These are all being done with replacement, hence the independence. Okay, and then the last one for this section, probability the second is full-time given that the first is full-time. So here I needed to separate them into second and first because it's a conditional probability. But because of the independence, you know, what you chose for the first person should have no effect on what the second person is. In other words, the probability the second one is full-time, regardless of what the first one was, is still the same. It's still 70 out of 100. And this is the thing that you could think about in the other presentation I gave, where, you know, we have this probability of B given A. Come on, pen. Over here. There we go. Come over here. Probability of B given A equaling the probability of the intersection A intersect B, or A and B, divided by the probability of A. But because of the independence, because these are independent, that numerator is the product of each probability separately. So that's the probability of A times the probability of B. And you can see these probabilities of A is just like in the previous video, these guys cancel out and we just get the probability of B. So in this case, B is the event of the second one being full time, and the probability of that is 70 out of 100. And that's a little tricky. So that's kind of where people need probably a little more understanding, or where the concepts get a little harder. All right, and then part 3, similar to what we just did, is just as we go through the problem, we're going to select the 2 people without replacement. So as soon as the first person is gone, it has the potential to change the total of people, goes from 100 down to 99. And then depending on whether we're picking the same type of person or not, it changes how many are available out of that 99. So here it does matter which one's first, but for transit, they're both probability that both take transit. So that's the probability of T and T. And the first one taking transit is 37 out of 100. I take that person out. So now there's only 99 people left. And how many people are left that took transit? Well, one that took transit is gone. So now there's only 36 total who took transit out of 99. So we're decreasing here both the numerator and the denominator. And I get 13.4%. The probability that the first is full-time and the second is part-time. So now I need to do them in order. The first is full-time, so that's 70 out of 100, just like before. But now that person is now out of the pool. So now we have 99 people left. And the question is, how many of them are part-time? Well, we didn't take any part-time people out, so we still have 30 part-time people, but we only have 99 people to choose from. So in this case, you know, only the denominator is decreasing by 1 because it's a different set of people we're choosing from. And that's 21%. 2 more parts. The probability that both are part-time students who drive. So, you know, part-time students who drive, that's actually an implicit and. They're part-time and they drive. So that's these, initially, that's these 21 students here. So the probability that the first one is part-time and they drive is 21 out of 100 times. And now the probability the second one is also part-time and they drive. Again, we have only 99 students left, but now we only have 20 who are part-time and drive because we took 1 out already. So times 20 out of 99. And again, you know, these numbers are decreasing because we are choosing these people with what's called without replacement. We are not putting them back in once we've taken them out, thereby changing the probability of the second choice. Okay, finally, the probability the second one drives given that the first one drives. So this is a conditional probability. And now, because we don't have independence, so why don't we have independence? When you take someone out, you change the totals. So, when you take one person away, that affects what the totals are. So here again, I don't think I want to try to use a formula. What I want to try to do is figure out what happens. So if you took one person out completely, there would be 99 people left. If you took a driver out, there would be 62 drivers left. So the probability the second one drives, given that the first one drives, well, there are 62 drivers out of 99. And then, where is that coming from? Why don't I have to use the formula? Well, I can use the formula. Probability, again, of B given A, that is the probability of A intersect B divided by the probability of B. And then, so A intersect B means that both has happened. So that's going to be 63 out of 100 for the first person driving times 62 out of 99 for the second person driving divided by the probability that the first one drives, which is 63 out of 100. And so again, just like the last problem, these initial probabilities are canceling, and we're left with this 62 out of 99. Unlike the previous part, the numbers went down by 1, both the numerator, the people who drive, and the total number of people, 99. And again, it's around 63%. And that gets us through this table problem. And I just kind of want to remind us, don't try to do the table problems without filling in these totals all the way across and down. So, and what you're wanting to check with these totals is that when you add the totals across and you add the totals down, that both totals then add up to the same amount, the 100. If you make a mistake in there, it'll make everything else kind of wonky. When we do this on the test, I'm not 100% sure. I might have some problems where I just want the answer, and I might have some problems where I want you to give me the notation in short answer form. So if you're including the notation, then that's at least 1 or potentially, well, usually 1 point, and the answers are usually worth 1 or 2 points depending on how involved they are. So the ORs, or the conditional probabilities, tend to be worth 2. Everything else in this problem 1 tends to be worth 1. In problem 2, because you're sort of doing things twice, again, the answers are worth 2 points, the notation is worth 1. So the notation itself generally is worth 1/3 of the problem. The answer is worth 1 or 2 points in and of itself. Okay, and that's using tables, and I will sign off.